Greetings and welcome, everyone. My name is Joshua Neidig. I am the SPS Manager of Business Administration. In my position, this really affords me the pleasure of working with our wonderful scientists like our guest speaker today. I'm delighted to have you all attend the CPAESS Discovery Seminar series. CPAESS scientists do everything from explore ocean depths to fly into hurricanes to heliophysicists modeling coronal mass ejections and those who unravel the mysteries of the Arctic. And we really want to share this information with the public, the NCAR, UCAR community, and our many colleagues at universities and agencies across the globe. And then just to orient you all today, we are using Slido so that you may pose questions for our speaker. You'll be able to find and access this tab at the top left of your screen. And then today, it is my sincere pleasure to introduce you to today's speaker, Dr. Baoqiang Xiang, who is a CPAESS Scientist 5 working with NOAA's Geophysical Fluid Dynamics Laboratory, GFDL. Bao's research focuses on numerical model development and large-scale climate variability and predictions. He is currently working on the development of the GFDL subseasonal forecast system and is co-leading the GFDL's next generation atmospheric model. Bao Xiang is also the 2019 recipient of the WWRP International Prize for Model Development. Today, Dr. Xiang will share his recent work with his seminar, How Predictable Are North American Summer Heat Extremes on the Subseasonal Timescale. Please join me today in welcoming Bao.
Thank you very much, Josh, for your introduction. So yeah, my name is Baoqiang Xiang. You can call me Bao. So right now I'm a CPAESS, UCAR.CPAESS employee. I'm very glad to give a presentation today to talk about the predictability of the subseasonal heat extremes over North America. First, I want to take this opportunity to thank many collaborators listed here. Um, as it's well known that heat wave is one of the most one of the deadliest weather-related hazard, and I'm listed several events here across the globe. You can see that heat wave events can induce substantial increase in mortality, and it will also put a huge pressure on the public health system. And it can also stress energy and water resources sectors. Of course, it can also potentially reduce the agricultural yield. Meanwhile, heat wave can also trigger some other compound extreme events, such as a wildfire and also droughts. So all those it will further amplify the societal impact of heat wave. So if we can predict, the important question is whether we can predict the heat wave on a longer time scale, especially subseasonal time scale. So this, if we can do that, this will have a huge value for the community to enhance their preparedness and also resilience. So here, first, I want to show you the subseasonal prediction. It's important, but it's also very challenging. This subseasonal, what I mean is like 2 weeks to one season, to 1 month, or 10 to 30 days. So I'm showing one plot showing this prediction of extreme heat factors from the NCEP CFS version 2 model. You can see the model actually has a very limited prediction. This extreme heat factor is a combination, is one of the metrics measures the heat wave. It combines the heat wave intensity and duration. You can see the current model has a very limited scale. It's just within 1 week, typically. So today I'm going to talk about the current status of both the dynamic model, and I'll also touch upon a little bit on the AI model prediction of heat extremes. Basically, I want to address two questions. The first is what are the dominant physical processes, physical sources of predictability for heat wave? The second question if we cannot predict within for the week 3, week 4, is there any window of opportunity that can extend our current predicted horizon? The model we're using the SPEAR, we call SPEAR subsystem prediction system. SPEAR is a GFDL model. It represents the simulation system for prediction and Earth system research led by Tom Davos. And this model is originally developed for mainly for seasonal to decadal prediction and also climate research. Here we extend this to subseasonal time scale. We have uh, the initialization is very simple. We nudge in the atmosphere circulation, temperature, specific humidity to measure 2, and also nudging the SST system temperature to NOAA data SST. There's no ocean data simulation, no land initialization, but the land condition will be adjusted accordingly because we have nudged the atmospheric conditions. So we run 20 years timecast from 2000 to 2019. Every 5 days, we run one case and integrate for 45 days. Each case, there's a 10 ensemble members. So this is a very large amount of data sets. We have used this model to start is like a Madden-Julian oscillation as shown in the left panel. The scale is quite promising. It's around 30 days. It's close to ECMWF model. And also we use this model to start the one-time atmosphere river prediction as shown in the right panel. We also use that to start the land for hurricanes, and another work is current under review about the stratospheric wave impact on the North America cold extremes. Uh, yeah, let's go back to talk about heat extremes. How do you measure the heat extremes? Here, the metrics I'm using is hot days. So hot days is defined as 90 when the temperature anomaly is above is 90 percentile of distribution. Uh, Here showing this June to August average the temperature anomaly threshold. You can see in the high latitude, relative high latitude, the temperature anomaly threshold is much larger than the lower latitude. That is because of the larger variability in the high latitude. This is from observation, but for the model, we use the model temperature anomaly distribution. Also use the same 19th percentile of distribution. Here I'm showing this correlation scale of weekly hot days. I'm using the weekly hot days, number of hot days within 1 week as a main metrics for this work. Okay, I'm showing the left panel is a week 2 prediction and right panel is week 3 prediction. You can see the prediction scale. Many regions is significant, but the number is not that high. Some region, you can see the west region, northeast, and especially in the coastal Gulf Coast region, that scale, southern Great Plain area, the scale is relatively high. Some region even 0.5, about 0.5, but generally the scale is relatively low. If you go to like a week 3, the scale is even lower. Only a very tiny region, the scale is about 0.4. So we want to understand why some region like Canada or Canada the scale is relatively low, but or the many region or US the scale is relatively high. What lead to this distribution of scale difference? So address that, we used this so-called average predictability time analysis, APT. APT is used to identify the pattern that will maximize the predictability. Here, the predictability is defined based on this equation, sigma tau represents the variance of Hanca's anomaly of individual members, and sigma climatology is the time average climatology variance. So if there's a large sigma tau, it means there's a smaller probability. So further, I will not go to the detail of this equation, but based on some derivation, it will become an eigenvalue problem. We can identify the major mode of that has a highly predictable, similar to EF analysis, but this is a EF analysis trying to maximize the variance. Here, the APT is trying to maximize the predictability. This shows first the two most predictable mode of weekly hot days from model handcast. There's no observation here. The first this shows the first mode is more like a dipole pattern with a large loading in the southern central US. The second mode, you can see there's a triple pattern as a and also this tilted dipole pattern over the US. So we also evaluated the prediction of these two modes. You can see the first mode during week 1 is about 0.8, during week 2 is about 0.6, during week 3, the first mode still have about 0.5, but second mode is less than 0.4. To further emphasize the importance of these two modes, we use these two modes and their corresponding time series to reconstruct the handcast anomaly. So you can see here is the correlation scale used to reconstruct the handcast anomaly only with these two modes. You can see the overall the pattern we can largely reproduce or the maximum in the southern US and one center here, but one center in the northeast North America disappear. It means some other mode can explain this. It's especially the I remember it's mode 6 and 7. But for the week 3, these two modes can well capture this pattern from the raw handcast, even slightly higher, in this region. So next, given this importance of this two mode, I'm going to further dive into the model physics. The first mode we call is the ocean force mode. Again, this shading shows that this MPM1 and contour shows a correlation with the 500 millibar J-proton height anomaly. Positive means high pressure, represent high pressure, low pressure, high pressure. High pressure, there's increased heat extremes. There's a clear wave train like a pattern. And if you look at the surface temperature, it's also very interesting. It is strongly coupled to SST pattern. This is largely represents the PDO, Pacific Decadal Oscillation, like a pattern. And it can extend to tropics. So this ST pattern can drive this wave modes through this baroclinic instability and also some anomalous convection, especially or this south of Hawaii can drive this can also drive this teleconnection through the wave propagation. So another point I want to I'll draw your attention is that for this mode, you can see the circulation cover a very large area, this high pressure, but the high predictability only constrained to the southern part of this this region, high pressure system. Why is that? So the right panel shows the soil moisture in the shading. You can see in the southern Great Plain area, there's a very strong suppressed negative moisture anomaly corresponding to a high temperature, high extreme currency. And this soil moisture deficit can further reduce the latent heat release and amplify the heat wave itself. And also the soil moisture is also can be an important predictive source because it can last a relatively long time. What causes this soil moisture anomaly? That is mainly because of precipitation as shown in this contour line. Another point I want to mention that the soil moisture, we show this is a concurrent soil moisture, but the soil moisture can be induced by the SST anomaly preceding this time, like during the spring or even winter can induce the soil moisture anomaly. So we argue that this mode is an ocean force mode that can be strongly influenced by land atmosphere coupling. Let's look at the second most predictive mode. I call this is an atmosphere internal mode. Why is that? Again, here is a correlation with Japan height at 500 millibar. It has this kind of wave train pattern, but another most prominent feature is there's a low pressure in the polar region and also high pressure in the Northern sector and also here. I did some significant tests. It's highly significant correlated with both the Arctic oscillation and North Atlantic oscillation. Um, but the surface temperature, there's not much surface temperature anomaly. But if you have a low, this is the acidic cold anomaly, but it could be a consequence of this circulation. And so that's why we call this atmosphere internal mode. It's not mainly driven by SST. Similarly, for the soil moisture anomaly, you can see there's a negative soil moisture here. It's correlated with this positive anomaly here, but in the northwest part, there's not much as a soil moisture anomaly. Probably it means that the land atmosphere coupling probably is less important in this region than the central and the southern, southwest, southeast US. We have shown that the scale is very limited for the week 3 prediction. So the question we may ask whether there's some window of opportunity. We have a better prediction scale for week 3 forecast. To address this, I'm showing this first mode observation versus prediction. Also, the first mode, you can see correlation is about 0.47 at week 3. We identified two groups. One is a good prediction group because it's a very the observation and prediction agrees quite well. Another is a poor prediction group. The observation we have an anomalies, extremes, but the model cannot predict an even negative sign. Here, I did not look at this quadrant because this is also important. This is so-called false alarm. This is one important topic for future research. Here, I'm mainly focused on these two groups, good prediction and poor prediction groups. This figure shows the observation and the prediction of the good prediction group, shading or the ocean at the SST, or the land is soil moisture, and also contour shows the circulation. You can see the SST is very predicted in the model on the subseasonal timescale. This is not surprising because SST has a long persistence. And the circulation, you can see there's a wave train like a pattern, but also have this wave train pattern. The model prediction can well capture this wave train, but the low pressure in the high latitude cover relatively small region than observation. But overall, I think it's not bad. And another feature I want to draw your attention is that there's a negative moisture anomaly, significant moisture anomaly, and the model will predict this. Here I'm showing the average during week 1 to 3 because the SST circulation and moisture are quite persistent as stationary. If you look at the individual weeks, there's no major differences. So how about the poor prediction group? You can see the SST very different, and it's to some extent it's a negative sign here. There's a significant warming here. Moisture, the model can predict the SST, but the circulation model fails to produce. And also, there's not much region. There's a significant moisture anomaly here compared with the good prediction groups. So it means if you want to have a good prediction at week 3, you need to have an optimal configuration regarding both SST, circulation, and soil moisture. Let's look at the second most predictive mode. Again, this is a observation and prediction. The model has predicts the low pressure in the Arctic region, and also this is circulation reasonably well. There's not much SST signal. But it's very interesting if you look at the poor prediction groups. It has a very beautiful atmospheric circulation wave train pattern from observation, but there's also a significant SST El Nino-like pattern or the tropics. The model can predict the SST quite well, but the circulation is there's a large mismatch. So why is that? It means like El Nino condition may degrade the forecast skill. This is somehow counterintuitive. We haven't looked at that in more detail, but this could be because during the La Nina or Nino decay summer, in observation there's not much acid forcing for the atmospheric circulation, but in the model you can see the high pressure or the tropics. It drives some kind of teleconnection. It will deteriorate observed circulation pattern. But again, this is a hypothesis. So this short summary for this part, we identified two dominant and physical source of predictability of heat extremes on the subseasonal time scale. The first mode is mainly represent the ocean force mode associated with the PDO-like SST pattern. And the second mode primarily reflect atmospheric internal mode that is very likely to link to Arctic oscillation and North Atlantic oscillation. And of course, the forecast, a subseasonal forecast is very challenging. It's typically limited to 1 to 2 weeks. However, a potential window of enhanced predictability, like a week 3 prediction, that could be possible if there's a quasi-sturgeon wave pattern and there's a soil moisture deficit coupled to some moisture deficit. Of course, SST is different for the first mode and the second mode. For the first mode, it's important, but for the second mode, it's less important. Here, for this first part, I am showing it's mainly some statistical results from the 20 years handcast. Let's move to just one case study. In the Northwest North America heatwave in 2021, there's many studies and for this event because it's really devastating and lots of damages. I'm showing the a dynamic model prediction and AI model prediction. Everybody is talking about AI. I'm showing some preliminary results here. So AI model, I'm using two AI model. One is ACE2, it's an AI2 climate emulator version 2. This is still a deterministic version. This model is trained from a ERA trained checkpoint. Just use 2 steps, and then we train this model using UFS replay dataset. 2, 4, 8, 12 steps using the period from 1994 to 2018. And the second model is a neural GCM. And this is a stochastic version of neural GCM model. And we also use the ECMWF S2S prediction and several sub-X models. We run 20 years handcast for the AI model, and all initialized at around June 15 during this period. And the target period is June 27 to 30. That is exactly the time for this heat wave event in the 2021. So this is almost it's roughly week 3 prediction. For the AI model, we use a persistent SST. There's no SST anomaly, only use the SST in initial condition. So anomalies are computed by subtracting the handcast climatology for both the dynamic model and also the AI model. I will see a little bit more about S2 model. It can well capture the subseasonal to decadal variation from a recent paper. It can capture like a tropic cyclone, Mediterranean oscillation propagation, and ENSO response. So here is some results showing this beyond weather time scale, like a week 3 prediction of heat wave from different models. Again, this observation, very strong high pressure and temperature anomaly here. This is dynamic model from 5 dynamic models. You can see it can capture some of the pattern and the high pressure, but the magnitude is much smaller than observation. Lower 2 panel shows the ACE2 and neural GCM. You can see the magnitude seem to be stronger than the dynamic model for both of them. But again, this high pressure system is mainly residing over the ocean, not moved to the land region as in observation. So here shows the time evolution for different model S2 neural GCM. You can see from different ensemble members. For S2, it will capture this first week or first 10 days. There's not much model spread because this is a deterministic version. After that, there's some spread you can see. But again, during the peak of this event, the model still underestimates. It's not within the spread for the model. The neural GCM also did a reasonable job. You can see it can capture the evolution, but the magnitude again is much weaker. So here shows a dynamic model, 5 dynamic model ensemble. For each is ensemble mean. I did not show the individual ensemble members. You can see the model seem to be magnitude much weaker and smaller than the both AI models. This further I'm showing the temperature, predicted temperature and Japan height from individual member and observations. You can temperature is in the Pacific Northwest in this box, blue box. Temperature close to 12 degree, and the model can predict the S2 can predict 6 degree. And neural GCM also did a reasonably good job, but EC model is about 3 degree. Some other model is like 4 degree. If you look at this is out of the sample individual members, the observation is out of the range of this ensemble members. But if you look at the Japan heights, actually it's very interesting. You can see the Japan heights seem to be better predicted than the temperature. And this anomaly is within the uncertainty range. Here, I'm further showing this the scat diagram between the 500 million bar Japan height anomaly and temperature anomaly. From this is observation. Diamond, black diamond is observation, and this is all members from both the dynamic model and the AI model. It's very interesting to see. You can see that they agree quite well. So it means that given the same Japan height, so we may predict the temperature anomaly based on this dynamic model and AI model, but observations seem to be out of quite a differ quite a lot at this uncertain range. If we use the linear regression, we may predict the temperature is only 8 degree, given this observed pressure anomaly. What does that mean? So probably it means our model may not well capture some physical processes like the boundary layer and land atmosphere coupling. Another possibility is that, as I mentioned before, because most of the model have this high pressure center over the ocean, and we have this anomalous convection from the polar region. It can reduce the temperature anomaly, but in observation, this center just quite collocated with a high pressure anomaly. So uh, uh, in the first part, I will talk about the soil moisture. Here is another example. I'm showing this precipitation anomalies before this peak of heat wave. From this S2 forecast, you can see there's a very long, persistent dry anomaly, less precipitation and dry anomaly before this peak of this heat wave. It means this dry anomaly will further amplify the heat wave intensity. Uh, this is very important, but this precipitation convection is also uh, can also be important because during the heat wave decay phase, the temperature amplified after the peak phase it will decay. What caused that? One of the factors is because of convection. The large instability and temperature anomaly will trigger the convection and will suppress and less as more clouds and enhance precipitation, increase the soil moisture. All these factors will be responsible for the decay of this heat wave events. But I also want to mention that the precipitation prediction uncertainty that will limit the heat wave prediction. What does that mean? Here shows a sky diagram between precipitation and temperature anomaly among 12 ensemble members during the decay phase, July 1st to July 5th. You can see they have a very good correlation, about 0.6. It means if there's a more precipitation, the temperature will decay faster, and less precipitation may persist longer. So there's a very large uncertainty of these individual members, and this can be because of the precipitation uncertainty, can be linked to precipitation uncertainties. So in other words, if we have a better prediction of precipitation, we may enhance the predictability of heat wave. So, but we all know that precipitation prediction is very challenging, and that's many factors like local processes and also remote process like Amazon River can influence the precipitation prediction. Yeah, this so it's if we can, yeah, we need some more effort to have a better precipitation prediction to ensure like this long lead prediction of heat wave. So for this event, whether we can, the first part we talk about the predictability source, and whether we can link these two parts. Again, this is showing the timer evolution for this event from ER5H to NeuroGSM on this multi-dynamic models. You can see during it's roughly in the first week, second week, third week, there's a strong pressure anomaly, and also in the northeast Eurasian region, there's a high pressure. So it's to model well capture this pressure, this pattern and temperature. And also there's a low pressure in the Arctic region. This did a very decent job compared with the ER5. Newer GCM have some capability, and dynamic model also capture some signal, but magnitude is weaker than the observation, and also S2 model. And you can also see the low pressure. These patterns seem to be well agree with the second most predictive mode derived from the SPEAR S2S system. This is circulation. You can see this circulation and the low pressure in the Arctic region. It seemed to be did a very decent job. But the other models seem to be missed this low pressure in the Arctic regions from both dynamic model and NeuroGCM. So here is a short summary. AI model seems to perform reasonably well for predicting this 2021 heatwave event. It can capture these underlying physical processes quite well. The second point I want to mention that precipitation uncertainty really limited the heatwave predictability. We need to have some more effort to better enhance the prediction of precipitation. For the future plan, given the importance of this land atmosphere coupling, and also our S2 model, it's a deterministic erosion. There's a less spread, ensemble spread. We will further incorporate soil moisture into the training using a stochastic version of S2 model. I have a final thoughts for this topic. I think this may not be only about the heat wave, but for this could be quite general for S2S prediction. I think AI and a dynamic hybrid model may offer more promising pathway. Of course, both the dynamic model and AI model have their own advantages and disadvantages. So we want to have a better uses of that advantages. So here are some examples. The first I used it's quite straightforward. We can use AI based post-processing for bias correction. There's already many studies for that. For example, it shows enhanced MGO prediction after the bias correction. The second example is use the SSD and the CIS field generated by the dynamic model to force this data-driven AI model. For example, we can use a SPEAR generate SST to force this S2 and NeuroGCM because right now the S2 and NeuroGCM, they are only atmosphere only model. We use a persistent SST. This, if we use a dynamic model produced SST anomaly, it may be more realistic and potentially enhance the prediction skill. The third one example is, all model, especially dynamic model, have this mean state drift issue. We need to deal with that. So rather than using the a climatology mean state adjustment, they can correct mean state, but we did some research, but it does not help the skill that much. So we may consider using this so-called state-dependent mean state adjustments within the dynamic model using some convolution neural network based on some recent research. So fourth one is also quite important, especially for extremes like a tropical cyclone, and that really depends on the model resolution. We may consider to combine the low resolution AI forecast model with statistic or and all dynamic downscaling to learn like for example the kilometer model X shields like a Hero H2 model. It learned the X shield model, 3 kilometer X shield model, and it can well capture this detailed structure of tropical cyclone and many other extreme events. So with that, I will stop here, and thank you very much for your attention. I would like to take any questions if you have. Thank you.
Then thank you so much for sharing your work, Val. We greatly appreciate it. And then now we will begin our Q&A portion of today's seminar. I'd like to direct everyone's attention to Slido to ask your questions. This will be in the upper left corner of your screen. And then just a reminder, as you're doing that, I would also like to invite you to please check out our webpage, cpaess.ucar.edu, for our upcoming seminars. Our next scheduled seminar is on March 18th, 2026 at 11 a.m. Mountain Time, with William Booth, a CPAESS scientist at the National Hurricane Center. We also invite you to find this talk and all past talks on CPAESS's YouTube channel. And then let's see what questions we have for you. Okay, I believe there's one question. Thank you for sharing your work, Val. Could you also say what improvement approaches you'll be working on next? I know you explained a little bit on that, but kind of could you go into a little bit more details as far as what's the top of your priority list?
Yeah, right now I'm working on like a, for the S2 model. I'm trying to have two versions of checkpoints of using one with a soil moisture training, another without soil moisture to understand in the land surface the importance of land surface condition, and also using using stochastic version of S2 model. Training model is relatively is expensive. This will take a little bit more time. Yeah, we for the dynamic model part, we are actively working on building a new generation atmosphere model and ocean model. Atmosphere AM5, ocean is OM5. So we will have a new we would hope to have a new version of forecast system in the next couple of years. Yeah. So again, that is something what we are working on now. So after that, probably we want to do some more hybrid AI and dynamic model forecast as listed here. Yeah, this will take, of course, every topic will take lots of effort, but it's a really interesting topic, I think.
Thank you for sharing that. That's greatly appreciated. Any other questions? If not, I would like to thank you all for coming to this UCAR-CPAESS Discovery Seminar. And remember, you can always go to our website to find out future talks at cpaess.ucar.edu. Here you all will be able to find a link to their talk after it's uploaded to YouTube. Perfect. There's one more question. Thanks for the presentation. I'm wondering how you plan to use the AI-driven model results for improving the dynamical models.
Um, yeah. So I think like so for the ocean, like Mom 6 group, they have used the AI model to understand the model biases. To what cause this model biases? It may given this to given this to further understanding the source, what is a potential problem for the parameterization and also different schemes. For atmosphere part. So we just started. So after we finalize our probably AM5 model. Oh, one thing I want to mention that we use some kind of auto-tuning methodology that has already been used in the NASA model. Uh, we 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 conduct some preliminary results to tune different parameters to have a best configuration. Use different metrics. Yeah, that is some ongoing effort for the model development. So yeah, in general, I think this will be really helpful. It can help model, especially for the subgrade parameterization. We can learn from the super high resolution model like X-Shield that does not have this like a deep convection parameterization. So yeah, there's something going on there. Yeah. Thank you for your question.
Thank you, Bao. We'd like to extend our sincere thanks to you for sharing your important work with us. This was very interesting, and I learned a lot, so thank you so much. And then I'd also like to extend some thanks to Alex Meyer of CPAESS, along with Fletcher Ryan and Chris Sepp of UCAR Multimedia Services for their invaluable assistance. I hope to see you all at our next CPAESS Discovery Seminar, and I wish you all a great rest of your afternoon. Thank you all for your time today.
Thank you very much. Have a good rest of the day. Bye bye.